Calorimetry. Calorimetry means heat measurement. It is the technique of calculating quantities of heat and final temperatures in processes of heating, cooling, and phase change involving a system of one or more bodies of matter. Although there could be other scenarios, the scenario we will analyze is a certain type of system that starts in an initial state and changes during a process to a final state. The initial and final states are the endpoints of the process. The type of system we consider is a closed set of one or more parts, which are bodies of matter or objects with mass such as blocks of metal, containers, water, ice, or vapor. The system is closed, which means that no matter or heat enters or leaves the system. The system is thermally isolated from its surroundings, whereas the parts are in thermal contact with each other and can exchange heat. Each mass consists of one substance with a specific heat C in each phase and latent heats for phase changes, and is initially at a uniform temperature in a specific phase, whether solid, liquid, or vapor. At the beginning of the process, a system is in an initial state with, in general, different parts at different temperatures. There must be at least one temperature difference in the system, otherwise nothing will happen. If all parts are at the same temperature, the whole system starts in thermal equilibrium and remains like that, so there will be no process to analyze. During the process, the system changes and passes through a series of intermediate states. Heat is exchanged between the parts, which experience temperature change or phase change, or both. At the end of the process, in its final state, all parts of the system are in thermal equilibrium at a common final temperature Tf, which is the temperature of the system. Here is the entire process represented with its endpoints. The task of calorimetry is to determine the various quantities of heat added to each part of the system in each phase so that the final temperature may be calculated, or other values if the final temperature is known. We are mainly interested in the initial and final states and the net quantity of heat added to each mass, rather than the details of what happens during the process. However, if any part undergoes a phase change, we must break the process for that part into steps, with the net quantity of heat specified for each step. In a temperature change step, the mass remains in one phase and changes its temperature due to a net added heat Q equals mc delta T. A partial phase change step takes place at a constant temperature, either the freezing point or boiling point of the substance, and a fraction x of the mass changes phase, so the heat added is Q equals x ml. A complete phase change step also takes place at a constant temperature, and all the mass changes phase, so Q equals ml. Let's take a look at various possible sets of steps. First, at the simple case of just one step. If the initial and final temperatures are within the temperature range of one phase, for example liquid, there is no phase change. During the process, there could be a change to another phase and back again, but we only consider the endpoints, which are in the same phase. If the initial and final temperatures of the mass are equal, at either the freezing point or the boiling point, then there could be a partial phase change, for example at the freezing point, or possibly but more rarely, a complete phase change in which just enough heat is added to change the phase of all the mass, but no more that would change the temperature. There will be two steps if the initial temperature is at a phase transition, for example the freezing point, and the final temperature is in another phase range, so that the mass first melts and then as a liquid increases its temperature, or starts as a liquid, changes its temperature, and then partially vaporizes. Each step requires a separate quantity of heat, so this one mass has Q1 and Q2 associated with it in the process, one quantity of heat for each step. If the initial and final temperatures are on either side of a phase transition, there will be 3 steps. In this example, a solid, such as a block of ice, first increases its temperature to the freezing point and has Q1 added, then melts with Q2 added, and finally the mass as water increases its temperature with Q3 added. At most, there will be 5 steps if the process crosses both phase transitions, with 5 associated quantities of heat for 2 phase changes and 3 temperature changes. We have looked at what can happen to one mass during the process. Now let's look at a system of more than one mass and at how the quantities of heat are used for calculations. Let's start with a simple system of 2 objects, 1 and 2, with masses m1 and m2, and a simple one-step process in which the objects exchange heat such that m1 loses a positive amount Q, which is transferred to m2. This either results in a temperature change of both objects, or in a partial phase change, or in a complete phase change in at least one object. Or both objects may experience a partial or complete phase change. We are going to treat the heat transferred to or from each object separately. For one transfer of heat, Q, we assign 2 quantities, one for object 1 and another for object 2, connected by an equation. This is the basic technique of calorimetry. Let the quantity of heat lost from object 1 be Q1, and the quantity of heat gained by object 2 be Q2. We assume that no heat is lost, so Q1 equals Q2. Both Q1 and Q2 are equal to the Q that is transferred between the objects. For this and more complex systems and processes, we may keep track of the various positive quantities of heat exchanged within the system, or we can treat every quantity of heat as signed and always added to a body of matter. Recall that if Q is positive, heat energy is gained by the object, and if Q is negative, heat energy is lost from the object. In this case, Q1 is the heat added to object 1, and Q2 is the heat added to object 2, and they are connected by the statement that Q1 plus Q2 equals 0. This is like accountancy, in which one transaction of money from one account to another is treated as 2 transfers, one a credit and the other a debit, such that the positive credit for one account cancels the negative debit for the other account. For a more complex scenario, we list each heat for each process for each object, and then we add all the heats together and set the sum equal to 0. We may express the sum of heats more concisely by using the sigma notation, so that's capital sigma adding up the heats Qi over the index I. As we have seen, a mass might go through more than one step during the process, and each step has an associated quantity of heat that is included in the sum. Note that we are not concerned with which object exchanges heat with which other objects, only in the net quantity of heat that is added to each object in each step of the process it goes through.